Blaise Pascal was a French mathematician, physicist, inventor, writer and Christian philosopher. He was a child prodigy who was educated by his father, a tax collector in Rouen. Pascal's earliest work was in the natural and applied sciences, where he made important contributions to the study of fluids, and clarified the concepts of pressure and vacuum by generalizing the work of Evangelista Torricelli. Pascal also wrote in defense of the scientific method. In 1642, while still a teenager, he started some pioneering work on calculating machines. After 3 years of effort and 50 prototypes, he built 20 finished machines over the following 10 years, establishing him as one of the first 2 inventors of the mechanical calculator. Pascal was an important mathematician, helping create 2 major new areas of research. He wrote a significant treatise on the subject of projective geometry at the age of 16, and later corresponded with Pierre de Fermat on probability theory, strongly influencing the development of modern economics and social science. Following Galileo and Torricelli, in 1646, he refuted Aristotle's followers who insisted that nature abhors a vacuum. Pascal's results caused many disputes before being accepted. In 1646, he and his sister Jacqueline identified with the religious movement within Catholicism known by its detractors as Jansenism. His father died in 1651. Following a religious experience in late 1654, he began writing influential works on philosophy and theology. His 2 most famous works date from this period: the Lettres Provinciales and the Penseus, the former set in the conflict between Jansenists and Jesuits. In that year, he also wrote an important treatise on the arithmetical triangle. Between 1658 and 1659 he wrote on the cycloid and its use in calculating the volume of solids. Pascal had poor health, especially after his 18th year, and his death came just 2 months after his 39th birthday. Early life and education. Pascal was born in Clermont-Ferrand, which is in France's Auvergne region. He lost his mother, Antoinette Begon, at the age of 3. His father, Etienne Pascal, who also had an interest in science and mathematics, was a local judge and member of the noblesse de robe. Pascal had 2 sisters, the younger Jacqueline and the elder Gilberta. In 1631, 5 years after the death of his wife, Etienne Pascal moved with his children to Paris. The newly arrived family soon hired Louise Delfault, a maid who eventually became an instrumental member of the family. Etienne, who never remarried, decided that he alone would educate his children, for they all showed extraordinary intellectual ability, particularly his son Blaise. The young Pascal showed an amazing aptitude for mathematics and science. Particularly of interest to Pascal was a work of Desargues on conic sections. Following Desargues' thinking, the 16-year-old Pascal produced, as a means of proof, a short treatise on what was called the mystic hexagram, Essai pour les coniques, and sent it, his first serious work of mathematics, to Père Masséna in Paris. It is known still today as Pascal's theorem. It states that if a hexagon is inscribed in a circle, then the 3 intersection points of opposite sides lie on a line. Pascal's work was so precocious that Descartes was convinced that Pascal's father had written it. When assured by Masséna that it was, indeed, the product of the son and not the father, Descartes dismissed it with a sniff. I do not find it strange that he has offered demonstrations about conics more appropriate than those of the ancients, adding, but other matters related to this subject can be proposed that would scarcely occur to a 16-year-old child. In France at that time, offices and positions could be, and were, bought and sold. In 1631 Etienne sold his position as second president of the Cour des Aides for 65,665 livres. The money was invested in a government bond which provided, if not a lavish, then certainly a comfortable income which allowed the Pascal family to move to, and enjoy, Paris. But in 1638 Richelieu, desperate for money to carry on the 30 Years' War, defaulted on the government's bonds. Suddenly Etienne Pascal's worth had dropped from nearly 66,000 livres to less than 7,300. Like so many others, Etienne was eventually forced to flee Paris because of his opposition to the fiscal policies of Cardinal Richelieu, leaving his 3 children in the care of his neighbor Madame Saint-Tot, a great beauty with an infamous past who kept one of the most glittering and intellectual salons in all France. It was only when Jacqueline performed well in a children's play with Richelieu in attendance that Etienne was pardoned. In time, Etienne was back in good graces with the cardinal and in 1639 had been appointed the king's commissioner of taxes in the city of Rouen, a city whose tax records, thanks to uprisings, were in utter chaos. In 1642, in an effort to ease his father's endless, exhausting calculations, and recalculations, of taxes owed and paid, Pascal, not yet 19, constructed a mechanical calculator capable of addition and subtraction, called Pascal's Calculator or the Pascaline. Of the 8 Pascalines known to have survived, 4 are held by the Musée des Arts et Métiers in Paris and 1 more by the Zwinger Museum in Dresden, Germany. Exhibit 2 of his original mechanical calculators. Though these machines are pioneering forerunners to a further 400 years of development of mechanical methods of calculation, and in a sense to the later field of computer engineering, the calculator failed to be a great commercial success. Partly because it was still quite cumbersome to use in practice, but probably primarily because it was extraordinarily expensive. The Pascaline became little more than a toy, and a status symbol, for the very rich both in France and elsewhere in Europe. Pascal continued to make improvements to his design through the next decade, and he refers to some 50 machines that were built to his design. Contributions to mathematics. Pascal continued to influence mathematics throughout his life. His Traité du triangle arithmétique of 1653 described a convenient tabular presentation for binomial coefficients, now called Pascal's triangle. The triangle can also be represented. He defines the numbers in the triangle by recursion. Call the number in the th row and th column Tmn. Then Tmn equals trademark 1, n plus trademark, n1, for m equals 0, 1, 2, and n equals 0, 1, 2. The boundary conditions are trademark, -1 equals 0, t minus 1, n equals 0 for m equals 1, 2, 3, and n equals 1, 2, 3. The generator TOO equals 1. Pascal concludes with the proof. In 1654 he proved Pascal's identity relating the sums of the pth powers of the first n positive integers for p equals 0, 1, 2, k. In 1654, prompted by his friend the Chevalier de Rémy-Acute, he corresponded with Pierre de Fermat on the subject of gambling problems. And from that collaboration was born the mathematical theory of probabilities. The specific problem was that of 2 players who want to finish a game early and, given the current circumstances of the game, want to divide the stakes fairly, based on the chance each has of winning the game from that point. From this discussion, the notion of expected value was introduced. Pascal later used a probabilistic argument, Pascal's wager, to justify belief in God and a virtuous life. The work done by Fermat and Pascal into the calculus of probabilities laid important groundwork for Leibniz's formulation of the calculus. After a religious experience in 1654, Pascal mostly gave up work in mathematics. Philosophy of mathematics. Pascal's major contribution to the philosophy of mathematics came with his De l'Esprit géométrique, originally written as a preface to a geometry textbook for one of the famous Petites Écoles de Port-Royal. The work was unpublished until over a century after his death. Here, Pascal looked into the issue of discovering truths arguing that the ideal of such a method would be to found all propositions on already established truths. At the same time, however, he claimed this was impossible because such established truths would require other truths to back them up. First principles, therefore, cannot be reached. Based on this, Pascal argued that the procedure used in geometry was as perfect as possible, with certain principles assumed and other propositions developed from them. Nevertheless, there was no way to know the assumed principles to be true. Pascal also used l'esprit géométrique to develop a theory of definition. He distinguished between definitions which are conventional labels defined by the writer and definitions which are within the language and understood by everyone because they naturally designate their referent. The second type would be characteristic of the philosophy of essentialism. Pascal claimed that only definitions of the first type were important to science and mathematics, arguing that those fields should adopt the philosophy of formalism as formulated by Descartes. In De l'art de persuader, Pascal looked deeper into geometry's axiomatic method, specifically the question of how people come to be convinced of the axioms upon which later conclusions are based. Pascal agreed with Montaigne that achieving certainty in these axioms and conclusions through human methods is impossible. He asserted that these principles can be grasped only through intuition, and that this fact underscored the necessity for submission to God in searching out truths. Contributions to the physical sciences. Pascal's work in the fields of the study of hydrodynamics and hydrostatics centered on the principles of hydraulic fluids. His inventions include the hydraulic press and the syringe. He proved that hydrostatic pressure depends not on the weight of the fluid but on the elevation difference. He demonstrated this principle by attaching a thin tube to a barrel full of water and filling the tube with water up to the level of the third floor of a building. This caused the barrel to leak, in what became known as Pascal's barrel experiment. By 1646, Pascal had learned of Evangelista Torricelli's experimentation with barometers. Having replicated an experiment that involved placing a tube filled with mercury upside down in a bowl of mercury, Pascal questioned what force kept some mercury in the tube and what filled the space above the mercury in the tube. At the time, most scientists contended that, rather than a vacuum, some invisible matter was present. This was based on the Aristotelian notion that creation was a thing of substance, whether visible or invisible, and that this substance was forever in motion. Furthermore, everything that is in motion must be moved by something, Aristotle declared. Therefore, to the Aristotelian-trained scientists of Pascal's time, a vacuum was an impossibility. How so? As proof, it was pointed out, light passed through the so-called vacuum in the glass tube. Aristotle wrote how everything moved, and must be moved by something. Therefore, since there had to be an invisible something to move the light through the glass tube, there was no vacuum in the tube, not in the glass tube or anywhere else. Vacuums, the absence of any and everything, were simply an impossibility. Following more experimentation in this vein, in 1647 Pascal produced Expériences nouvelles touchant le vide, which detailed basic rules describing to what degree various liquids could be supported by air pressure. It also provided reasons why it was indeed a vacuum above the column of liquid in a barometer tube. On the 19th of September 1648, after many months of Pascal's friendly but insistent prodding, Florent Perrier, husband of Pascal's elder sister Gilberta, was finally able to carry out the fact-finding mission vital to Pascal's theory. The account, written by Perrier, reads: "The weather was chancy last Saturday, but, around 5 o'clock that morning, the Puy de Dôme was visible, so I decided to give it a try. Several important people of the city of Clermont had asked me to let them know when I would make the ascent. I was delighted to have them with me in this great work. At 8 o'clock we met in the gardens of the Minim Fathers. which has the lowest elevation in town. First I poured 16 pounds of quicksilver into a vessel, then took several glass tubes, each 4 feet long and hermetically sealed at one end and opened at the other, then placed him in the vessel of quicksilver. I found the quicksilver stood at 26 and 3½ lines above the quicksilver in the vessel. I repeated the experiment 2 more times while standing in the same spot. They produced the same result each time. I attached one of the tubes to the vessel and marked the height of the quicksilver and asked Father Chaston, one of the Minim brothers, to watch if any changes should occur through the day. Taking the other tube and a portion of the quicksilver, I walked to the top of Puy de Dôme, about 500 fathoms higher than the monastery, where upon experiment, found that the quicksilver reached a height of only 23½ lines. I repeated the experiment 5 times with Kerr, each at different points on the summit, found the same height of quicksilver in each case. Pascal replicated the experiment in Paris by carrying a barometer up to the top of the bell tower at the Church of Saint-Jacques de la Boucherie, a height of about 50 meters. The mercury dropped 2 lines. In the face of criticism that some invisible matter must exist in Pascal's empty space, Pascal, in his reply to Estienne, gave one of the 17th century's major statements on the scientific method, which is a striking anticipation of the idea popularized by Karl Popper that scientific theories are characterized by their falsifiability. In order to show that a hypothesis is evident, it does not suffice that all the phenomena follow from it. Instead, if it leads to something contrary to a single one of the phenomena, that suffices to establish its falsity. His insistence on the existence of the vacuum also led to conflict with other prominent scientists, including Descartes. Pascal introduced a primitive form of roulette and the roulette wheel in his search for a perpetual motion machine.